Okay.
So medium.
We have so the Moore theorem, and that yields this bounds on the hypergraph Turan problem. For graph case, if you use this, then again using this you can derive the bounds on the Turan number, which is actually tight. So this actually gives, so okay, maybe it's better to just write it this way. So what's this? When r equal 2, this provides this upper bound on the extremal number on clique. And from Eridis Simonovich, we know that this is tight. I mean, asymptotically tight up to this little one term. And because of this, I mean, the graph lemma here actually provides a supersaturation. So if you are above extremal number, then you have this many copies of clique. But this bound in general for RL3 is not tight. Hence the above one, this counting one, does not provide a supersaturation. So it provides a lower bound on the number of cliques above certain threshold, but that threshold is bigger than the Turan threshold. So there is gap between these two thresholds. We don't know how many cliques can we, guarantee. So this theorem does not guarantee many cliques in there, so it does not imply supersaturation. Anyhow, so as I mentioned, this is not tight. And how do we know it? We already have discussed before that the Turan conjecture that in 1941 conjecture that the four vertex clique of three uniform cliques have the extremal number roughly 5/9 times n choose 3. However, if you compute the value here, then what? When can we ensure that this is positive? So this is positive if n3/n2 is bigger than 2n/9 plus some constant. I'll forget about constant for now. Then n3 is bigger than 2/9 n plus constant times n choose 2. That's what? 1/9 n cube, which is 6/9 and choose 3. So that's roughly what? The bound we get was 6/9, almost 6/9, but the conjecture is 5/9. So that is this gap. And in fact, there are upper bounds on this number. Best known upper one is something like 0.56 something and choose 3, which is smaller than this 6/9. So this shows that this is actually not tight. And we have already discussed before, but let me repeat it. The lower bound of 9/5 comes from the following construction. You take n over 3 vertices, v1, v2, v3. And how do you put the edges? You put the edges which use 2 vertices and 1 vertex here, and 2 vertices, 1 vertex here, and 2 vertices, 1 vertex here. Then, I mean, you can check that this does not contain a copy of 4 vertex clique. And the number of edges is roughly 5 over 9, hence n choose 3. Okay, so this provides a lower bound. Then natural question is that for other values other than 3 and 4 here, what lower bound do we get? So Sidorenko in 1981 proved the following lower bound, generalizing the above construction. That you have 1 minus I minus 1 over s minus 1 to the I minus 1. So in fact, when this is s, this is r, and what? 1 minus 2 over 3 squared. So you get the 5 over 9 here as before. So this is a generalization of this lower bound. So what we want to do, we will construct an R uniform hypergraph H with at most this many edges, so that every set of S vertices contains an edge. So this is what? This is going to be the complement of what we want. Then we take complement of this H proves the theorem. It provides a construction for lower bound of this. So how do you do it? We consider balanced partition, so an equipartition. Here, equipartition means that you partition the vertices so that the size of them is as close as possible. So all of them have size either n over s minus 1 floor or ceiling. And what? For each, say, subset of size R, we add this E as an edge of H if and only if there is some J such that the following holds. So what was the construction before? So here is that you have 2 and 1, 2 and 1, 2 and 1. So we consider cyclically. So 1, 2, 3, 4. It starts from 2 and then 1. So that's the That's the construction. And then we now want to generalize this in the following way. But there was a mistake that I made. So here I forgot to mention that okay, this type of thing is an edge, and as well as this type is an edge. So one vertex from here, and then one vertex from here, one vertex from here. So those two are the edges. But okay, to be more consistent with the previous, the example that we want to consider, let's take this one. So in here, the example is you take edge from one vertex, one vertex from this part, as well as you have say one vertex here and then two vertex here. So before the previous one, and it has two. The first one has two, and then second one has one. But let's split two from the later, and then one from the earlier. So that's the example. And so here we are considering a complement. So in here, if you take complement, what do you get? It's either an edge here. You have two things. Either all three come from one part, or two from one part and then one from the subsequent part. So that's what we have. We generate this into this. What is this? So what this means is that there is part J, which contains at least two elements, and then this plus the next one all together has at least three elements, and this, and then next one has at least say four elements, and then next one. So this all together has at least five elements, and so on. So that's exactly what's happening here. Starting from here, it has at least one, at least two, and at least three. So you have three. And here you have at least two, here at least three. So you do that for k at least r minus one. So what it means is that starting from here, you write down 2, 1, 2, 0, 1. Then this number is at least 1, this one at least 2, and this number is at least 3, this number is at least 4, this sum is at least 5, this sum is at least 6, and so on. If that's satisfied, then you put it as an edge of H. Okay. Then what? If we pick a S set, it's from say V1 to Vs minus 1, then we can show that there exists, say, so that for any k, this holds. So this, let's say, star. So in other words, if you have S vertices, then here you have S minus 1 part, and then you choose S vertices. Then this satisfies this condition, so that you can choose on a set of I vertices which forms an edge. So if we know this, then that's proving this part. And why this is true? Because you choose from this S minus 1 set, you do this, so you what? We choose J as random. Then you can compute the give me a moment. So you can choose this as random and then show that with positive probability it holds. Yeah, I'm sorry that I was thinking some random argument could work, but I was wrong. Sure. But this proof is not difficult. And roughly as follows, I will not write it rigorously. So for example, let's say your set is like B0, B1, B2, B3, B4. You choose like 1 vertex, 0 vertex, 2 vertex, 2 vertex. So S is 5. And what you do is you pick like points 0, 1, and you add those two, then that's 2, 1. I mean 1, 1. Then you add those, and then that's 3. So you move up by 2, and you move up by 2. So let's say you have this. And since it's recursive, so we are taking circular, so, and this comes back. Let's repeat this. So you have this, and you write, you concatenating that. Okay, and so what? You yeah, let's do this. And then you draw this line. And this line is like sorry, you draw this line. And this line has the slope 5/4, or generally x over x minus 1. And what we want in here is that these points are above this line. So this is saying that we want this to be above this line, and this point to be above this line, and so on. Okay, let me correct myself. So this to be above this line, that's what we want. And this summation, so this to be above this line, and this summation to be above this line, and this summation to be above all on this line. But in this case, that's not good. But what we can do is that by readjusting the starting point. So here, what's the lowest part from here? This, right? So if we move it in this way, then now you are satisfied what we wanted. So in terms of this line's perspective, you choose the lowest part and then you move from here. And then shift things. So in this case, you shift twice, then 2, 2, 1, 0. Then now this condition is satisfied. Means that these points are all above this line. So you can make it rigorous. I will not make it rigorous, but by using this idea, I mean, you can choose your starting point here. So you can redraw this by, you start from here, then what, 2, 1. Your line is here, and you make sure that all these points are either on this line or above. That's same as this inequality. So yeah, sorry for my confusion. So this shows that this hypergraph actually has the property as we desired here. Now what we want to show is that the number of edges is correct. So let's consider the following and how we to count this. Let's say you have an R tuple, x1 to xr, and we say that it is of type j, c for some j in here, and some c, which is tuple of c1 to cr, and what? Let's write it as bold c. If xi is in bj plus this ci, okay, then each r vertices tuple of r vertices you have type, and we say that the C is legal if this way of choosing satisfies what we want. So what it means is that if any R tuple of type J, C produces an H x1 to x1 of H. In other words, it satisfies this top. Okay, then for fixed J, we can count the number of legal C. There are r-1 to the r-1 legal C. We can show this. First, what we know is that this C has to be chosen from this set. So all the Ci must have value between 0 and r-1, r-2. Because otherwise, it's star. So you have V0, V0 plus 1, Vj plus r-2, Vj plus r-1. Here, we know that the S is at least R. So at least R plus 1. So otherwise, so we can assume that this holds. Otherwise, I mean, if it's just an edge. the extremal number of one edge is not so interesting. So in here, what? If we satisfy this top, that means when k is r minus 1, then you count the number of vertices here. That should be at least r. That means this should be empty and next one should be empty as well. So this C, let's say each CI is between 0 and 1 to s minus 2. So it doesn't wrap around to come back to J. And everything has to be here, so this is obvious. And we consider cyclic commutation. Meaning that is, let's say this be C prime 1 to C prime R, where the C prime I is Ci minus L mod R minus 1. So if original one was like 1 from here to, let's say original one is like 1, 2, 1, 3, 2, that means what? X1 is here. And X2 is here, X3 is here, X4 is here, X5 is here. And when L is 1, then what you get? And 0, 1, 0, 2. Let's say you take negative 2 and shift C R minus 3 is what? This is R minus 2, 0, R minus 2, 1, 0. So its clique shift is X2, X5 moves from here to here, and X1, X3 moves to here, and X4 moves to here. So now we kind of see how this cyclic commutation works. So in this red case, you get this cyclic shift. And this black case, you get this. Then what? Note that we consider all this shift. This forms a group, meaning that the group may not be a good word. I'm not talking about the algebraic structure group. It's let's just say group. So we group them. We group this R minus 1 of them. So out of all this, you group this R minus 1 of them. And in each group, we can show that only one of them is legal. Why? If two of them are legal, they shift of say C0 and shift of CL are both legal. If that's, if two of them are legal, then we can assume that one of them is 0 and then the other one is L. Otherwise, you just change some some numbers in the following argument, then what? We consider x, which is j, c type of type jc for some j, then what? bj together with bj plus l minus 1. This contains at least l plus 1 vertices in x1 to xr because this is legal. And also because this is legal, you know that the bj plus l dot 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 to bj plus r minus 2 is together contain at least r minus l vertices in here because they are legal. But these are disjoint. But together they contain what? More than r. A contradiction. So each group contains at most one legal C. And then how many of them are here? So you have r minus 1 of them. And then there are r minus 1 to the r minus 1 of them. And then you group r minus 1 in a one group. So here there are so this is r minus 1 to the r. It's many. So at most legal C. So now what? For every legal C, there are s minus 1 choices of J and fixed C and J. What? Once you know this type, so starting from this Bj, you know how many. So, I mean, you know that the x1 has to go to here and x2 has to go to here. x3 again has to go to here. x4 go to here. x5 has to go to here, etc. If you know this, then each time you move it here, move it to here, what's your choice? You have 1 plus little of 1 times n over s minus 1 choice. There are some restrictions that once you put x1 here, later when you put x3 here, you have to avoid this vertex. But that's observed in this little one term. Essentially, when n is large and then everything else is constant, you have this many choices, and you have to do r time. So this is the number of choices of the choices of x of type j, c. So the number of r tuple where this one is an h is you multiply it then you get what? 1 plus little of 1 times r minus 1 over x minus 1 r to the 1 and to the r. And what? Each edge is counted r type r factorial times here. So the number of edges in H is if. And that's exactly what we wanted. You take the complement, then you get this statement. And that finishes the proof. So we have this upper bound and lower bound on the extremal number of this clique. Okay, so yeah, that's all for today. Yeah, we have discussed about the hypergraph theorem bounds. And I will add a bit more about some recent bound on the lecture note. So you can check them to see what's some other bounds known. Okay then, thank you for listening. I will see you in next video.